Our group project is called Brain Change is Inevitable, Modeling Representational Drift Using Deep Convolutional Neural Networks. I'm Shelby, and my other group members were Robert, Sudhanshu, and Varun. Representational drift is the phenomenon that neural representations change during the presentation of the same visual stimulus, and that this change occurs over time, and that time can be as little as, tens of minutes. Representational drift has been observed in multiple sensory systems, such as olfaction, vision, and even during learning. And many scientists have suggested there may be different mechanisms that cause drift, whether that be changes in excitation or inhibition of neurons, differences in synaptic connectivity, influences of behavioral variability in animals or humans, and changes in population coding within the brain. But we can only model a few of these potential mechanisms because of the limitations of artificial neural networks. So for our project, we were inspired by an Allen Institute dataset that was looking at visual response properties over time, as well as recent work done by Aiken et al. Investigating the geometry of representational drift. In that work, they found that node dropout within their convolutional neural network most closely resembled representational drift that you see in real neural populations. So we sought to compare data from the Allen Brain Institute to test that hypothesis further, looking at node dropout.
Here's the first method we used. We trained a deep convolutional neural network on CFAR 100. CFAR 100 is a task where your model has to identify which of 100 classes a given image belongs to. Once trained, we broke off a bit of the test set and used it as an analog of the natural movie that the real mice had seen. Then we trained the convolutional network on that movie 30 times in a row while sampling the activity of artificial neurons from multiple layers for later analyses. We also periodically checked that the behavior of the network was stable using the remaining test set images. And here's the results from that method. We've got the real mice data on the left. Each block is a different region of the visual system that shows drift. We're looking at average neural activity given a movie and comparing it to the same movie shown a short time later. So the values are always strongest across the diagonal because one movie's neural activity is being compared to itself, which is going to have the highest similarity as measured here by the Pearson's correlation coefficient. The neural activity changes even over the minutes it takes to show the mice the movie 30 times. You can see this trend in the furthest left column in any given brain region. As we go down that column, we are comparing movies spread further apart in time, and we see a rather slow and continuous decorrelation. The data from the artificial neural network is shown on the right. It is strikingly different. The similarity between representations in different movie repeats is very low almost immediately.
The Allen Institute paper trained their network on another dataset, which was CFAR 10 dataset. So to try to reproduce their results, I retrained our network on the CFAR 10 dataset. And I also wanted to see that maybe if we pull across all categories of stimuli, maybe there's a null result. But if we look at each category separately, maybe we get some sort of a drift. So I took 3 kinds of networks. And I'll explain what kinds, but yeah, I'll explain the general idea first. So I took one network and computed the correlations of representations. That is the last network response, last layer response for across all the classes as we train more and more. So on the y-axis is the class-wise correlation. On the x-axis is the difference in epochs from the reference network. So we have one network and then 15 subsequent retrainings of the network. And we have 3 kinds of network. The first is the dropout network, which was found to be the best by Allen Institute for reproducing drift. And to benchmark it against what is expected just because of training, we have one network without dropout, and another network which stabilizes the performance of the network, but without using dropout, which is L1 regularization network. So what we see is if we don't have dropout, the training is still not stable. So we get the most drift. So at least drift is the drift we get from dropout is not more than what would expect from a network which is still in training. So we took two networks which have mostly stabilized. One is dropout, the other is L1 regularization. And both these methods, they try to stabilize your testing accuracy. So we see that while their performances are similar, so the error bars per category are similar. I mean, at least they are better than the middle thing. But the error bars are similar, but it is still higher in the bottom right network, which is the L1 regularization network. So dropout uh, gives you less fluctuation than other regularization method, as well as the absence of dropout. So we weren't able to reject the null hypothesis that dropout induces more drift than would be expected just by random fluctuations in the network.
So to summarize, representational drift is defined as the slow and steady change at a population level of the representation of a given stimulus in a directional manner, implying that, and at a long time scale, implying that this change can't be really explained by repetition suppression or general neural variability. It's been posited as a method to prevent biological networks from overfitting. The analog for that in artificial neural networks is no dropout. And one of the papers that we were looking at essentially was able to induce representational drift in their network using no dropout. So we tried a few different networks and a few different ways of training them. And our findings do not corroborate the notion that no dropout causes representational drift slowly and steadily over time. It's kind of like the tortoise and the hare. We found much faster fluctuations across the board, and in some cases, less fluctuation than you would just expect from training. And so that's kind of interesting. One of the potential issues could be that due to time constraints, we couldn't retrain very large recurrent networks over and over. So we chose a version that had no recurrence, essentially. So it's not a really faithful model of any biological sensory system. So potentially we would see more drift, and recurrence has often been discussed as a key element of sensory processing. So maybe it's a key element of inducing representational drift too. The other is the training phase. Now, there are many different phases you could train these networks. You can pre-train them and then fine-tune them and so on. And so maybe if we played around with that, we could have potentially seen some difference. But that is all she wrote. And with that, we'll take questions, I guess. Assuming we have time. We do have time, right, Christian?
Yeah, thank you. Thank you for the presentation. Is there any question for this group?
I have a quick question. So you put up here some of the possible differences. What do you think would be necessary, or like what would be your next step if you wanted to try to be able to test this further? What would you want to add in?
I can give my answer, and then I think I'll turn it over to the guys who actually did the training. I would probably have started with one of the largest networks. So the network that we took off the shelf was from the CoreNet family. These are from Jim DiCarlo's lab. They are modeled after the primate ventral visual stream, and there's many different versions of them. I think there's 4 specifically, and we chose the tiniest baby one that has no recurrence and has the lowest brain score correspondingly, and so on. So I'd probably start by just retrying everything on a bigger network that actually had recurrence. That would probably be my first way to go. And then potentially train and test it over many, many more epochs than we actually had time to do.
Yeah, more realistic spine turnover than just random whole dropout of a neuron could be implemented.
Dropout is also something that only exists during the training and not really during the testing. So if that could be something contributing, we just want to make sure to rule out dropout, because the other paper, it has shown that dropout shows you signature of drift, but they haven't really benchmarked it against just random fluctuations in a network. So we want to do that first.